Hello, we are Team Vicharaka. We are a passionate group of undergraduate students from Indian Institute of Science. This is our second generation rover, Vyoma.
Our team operates under a team lead, supported by a technical lead for engineering integration and a management lead for operations. Together, they oversee 5 specialized subteams. The mechanical team designs and manufactures the rover and the robotic arm.
Software team, which is responsible for creating the autonomous stack for the rover.
While the electronic team handles complete electrical architecture, including power distribution, system wiring, and custom PCB design for both systems. We have a dedicated drone sub-team focused on drone design, manufacturing, and flight operations. Finally, our bioscience team is in charge of developing the biomodule and creating our scientific research plan. This structure ensures every critical subsystem has a dedicated expert team driving it forward.
Returning to the European Rover Challenge for the second time, we see ERC as much more than just a competition. It is a chance to apply the lessons learned from our previous participation, compare ourselves against international standards, and continue growing as a team. Building a complete new rover from ground up, we embrace every difficulty as a chance to learn, innovate, and inspire. We are once again very much excited to be the part of ERC community and to contribute towards planetary exploration.
This year we have completely redesigned our rover, switching from a 6-wheel rocker bogie mechanism to a 4-wheel rocker mechanism, with each of the wheels having individual steering.
Built on a modular sheet metal chassis, reinforced with aluminum extrusion, the rover boasts a track width of 91 cm, a wheelbase of 82 cm, and a ground clearance of 26 cm. To maximize maneuverability and power, we paired stepper motors with planetary gearboxes for precise independent steering while driving the system with high-torque DC motors. We engineered custom 3D printed wheels featuring a rigid PETG inner shell with a flexible TPU 68D outer layer with an S-spoke design for optimal grip. By combining these larger high traction wheels with our upgraded steering and powertrain, the rover is fully equipped to conquer the harshest terrains with ease.
For the electronics, this year our primary focus was on enhancing reliability and compactness. At the heart of the subsystem, we have 2 custom-designed power distribution boards featuring a pop-up mechanisms. The boards have a vertical slot into which various submodules like motor drivers and buck converters are installed, which can be easily removed in case of any faults. We designed 25 ampere rated closed-loop brush motor drivers controlled by STM32F4 microcontrollers. Our boards offer much greater reliability and have safety features like undervoltage, overcurrent, and thermal failsafe mechanisms. Our boards also possess superior efficiency compared to commercial units and at the same time provides precise telemetry over a CAN bus network. The development of a second revision of the same is in progress. The stepper motors responsible for steering and the robotic arm control have absolute encoders and are controlled by industrial-grade closed-loop Rhino drivers, enabling incredible precision in their movements. The rover is powered by 2 custom-built 22.2-volt lithium-ion battery packs, providing up to 2 hours of continuous runtime.
The navigation system is designed to traverse complex planes autonomously. At its core, the system relies on visual inertial odometry, which uses a RealSense depth cam and a 10x IMU. To map the surroundings, we integrate a unitary 4D LiDAR. An extended Kalman filter fuses the VIO output, the LiDAR data, and wheel odometry to maintain a reliable pose and enable dynamic obstacle avoidance. For mission objectives, the rover uses image processing to recognize ARUCO markers and prescribed targets. If a target is not visible at the given GNSS coordinates, the system initiates a spiral search algorithm to scan the surrounding area until the objective is acquired.
Our rover uses a consolidated dual-layered heterogeneous network system designed to maintain high quality of data stream for autonomous and manual safety overrides. The system architecture is built upon ROS2, which acts as a software backbone to ensure all perception, planning, and control modules communicate with minimal latency. The high bandwidth communication is handled by an Ubiquiti rocket AC 5.8 GHz paired with a 13 dBi Omni antenna on the rover and a 19 dBi sector antenna at the base station. This link utilizes the AirMax TDMA protocol to provide deterministic transmission windows for real-time HD video and bidirectional cross-to telemetry. And NVIDIA Jetson Orin Nano serves as the central compute hub, orchestrating high-level perception and mission logic. It interfaces with dedicated microcontrollers, a Teams 4.1 for low-latency drive actuation, and a STM32 for the robotic arm control via micro-ROS. A discrete 2.4 GHz Skyride Astral system serves as an independent deadman switch. This link provides a robust hardware-level backup for manual control and emergency stops with a tested operational range of up to 2 kilometers, even in non-line-of-sight conditions.
To assist Vyoma, we have an autonomous companion drone weighing 1.5 kilos, built on a lightweight carbon fiber quadcopter frame featuring a hybrid tractor-pusher propulsion mechanism. Driven by four 935 kV brushless motors, the front tractor propellers pull undisturbed air to maximize thrust efficiency, while the rear pusher propellers generate a balanced thrust vector that minimizes aerodynamic turbulence around the central fuselage. This ensures stability and agile maneuvering even during high winds. Autonomy is split across a Pixhawk flight controller, which handles low-level stability, while an onboard Raspberry Pi processes a downward-facing Intel RealSense Steps camera and a 1D LiDAR to detect probes and landing sites. Our custom software stack executes real-time 3D terrain generation and Aruko marker detection using the DepthCam feed. In case of a system alert, the drone uses this terrain data and executes a radial landing patch search algorithm. It continuously checks the patches for the deviation of its normal vector and roughness to find the closest safe patch and navigates to it using the flight controller's IMU sensors instead of GPS to ensure a safe landing.
Our robotic arm consists of 6 degrees of freedom, with each joint driven by closed-loop stepper motors coupled with harmonic gearboxes. We extensively used finite element analysis to achieve optimized joint designs, ensuring structural strength while minimizing weight. This configuration provides us with precision better than 1 arc minute. The shoulder joint delivers 230 Nm and the elbow joint provides 120 Nm. Even at full extension of 1.2 meters, our robotic arm can lift 8 kilos of payload with ease. With dexterity and precision in hand, our arm can perform many agile tasks. With strategically placed cameras, it can detect multiple objects, keyboards, and Type-C Arco markers, etc.
The bio module is a multifunctional science system designed for control and contamination-free handling. It is primarily composed of 3 subsystems: the deep sampling unit, the surface sampling unit, and the chemical testing unit.
For surface sample collection, the rover is equipped with a 5 degree of freedom secondary manipulator capable of acquiring soil and regolith samples from the terrain. The collected material is deposited into 5 onboard sample containers, each integrated with load cells to accurately measure the mass of collected samples, along with TDS sensor and soil moisture sensor for real-time chemical and environmental analysis. A portion of the collected soil is retained for storage and further analysis, while the contents of the remaining 4 containers are combined to prepare a soil solution. This solution is subsequently transferred to the chemical testing unit using peristaltic pumps, ensuring controlled and contamination-free fluid handling. The chemical testing unit is designed to perform 4 distinct chemical analyses simultaneously on 4 separate soil samples. In addition, the bioscience module incorporates a dedicated water sampling container capable of collecting liquid samples for pH analysis.
We have developed an efficient deep sampling and storage system for Martian soil, which can take down to 32 centimeters. Our drill is composed of 3 motors, one stepper motor to lower the auger using a release screw mechanism, another stepper to rotate the auger, and one servo for the 4-petaled iris mechanism to contain the soil securely inside the metal sheet. The metal frame provides the strength and rigidity required to drill hard soil.